So, welcome back to our projective geometry lectures. This time we will talk about homogeneous coordinates. This is chapter 2 in our lecture, and it's chapter 3 in the book Perspectives on Projective Geometry. And homogeneous coordinates are a way of creating projective planes from fields, and you will see the mathematics behind it is not extremely subtle, but it's extremely far-reaching. So let's start like in a generic maths lecture. Let K be a field. So you may think of K as being any field, and I want to show you a construction how to get from K to a projective plane. And the idea behind that is to do homogeneous coordinates. And for doing though, we define three sets, P, L, and I, that represent what we do in projective planes from our K. So first of all, we define a set PK, which we define to be the following thing. We take the three-dimensional, so be careful, it's three-dimensional, not two-dimensional. The three-dimensional vector space over K, we take away the zero vector. So on my slides, this bold 0 should represent the zero vector, and we identify multiples of those vectors that only differ by a non-zero factor. So you have written what I mean in a different way. So take a point P, which should be, so here you define equivalence classes, and this here is one representative of this equivalence class. Take that from the vector space, but not being the zero vector, and then you say everything that differs by P just by a non-zero multiple should be in the same equivalence class, and those equivalence classes will be called the points of our projective geometry. Now we do the same thing, and literally the same thing, for our lines. We define a set L to be, well, just the same thing. Take the three-dimensional vector space, take away the zero, and identify non-zero scalar multiples. So for each L that we get from that, there will be equivalence class consisting of all scalar multiples of this vector. And we call these equivalence classes here the lines. So once more, these here are the points, and these here are the lines of the geometry. Now we have to define when a point and a line is incident to each other. And this here is the definition of the equivalence relation. So if we have one equivalence class for the points and one equivalence class for the lines, we call them incident if the scalar product, the standard canonical scalar product between the point and the line coordinate equals 0. So if you want to think about K being the real numbers, this means that the representing vectors of L and P are orthogonal to each other. But we're now at at a general field K, and you shouldn't think too geometrical at that point. You should spend a moment to convince yourself that this definition here is indeed well defined. So if you replace P or L by a suitable multiple of itself, it generates the same equivalence class, but you see replacing P or L by a multiple of itself won't change this relation due to the linearity of the standard scalar product. So Now we look at these P, L, and K, and P, L, and I, and the important thing we now see about them is that this triple for any field indeed is a projective plane. And actually it's close, it's very simple to prove. So let's prove that, and this is theorem 3.1 in the book. So what we have to do, we have to prove theorem A1, A2, and A3. And you remember A1 was for any two distinct points, you get a unique line incident to them. And let's see how that works. So take two equivalence classes generated by two vectors P and Q that are not the same. If they are not the same, this implies that P and Q are not scalar multiples of each other. Because if they were scalar multiples, they would generate the same equivalence class. So different equivalence class results here in linear independent vectors P and Q. But this means that this matrix here has full rank 2, and that this system of equations I wrote here, which is essentially a standard scalar product of this vector times this and this vector times this, has a one-dimensional solution space. A one-dimensional solution space is exactly an equivalence class in our world of lines. We have to be a little bit careful. We have to take the zero vector out of that solution space. But then this L that we get here can be taken as, well, if this here is L, then the unique line incident to both of them would be the corresponding equivalence class of L. This essentially already proves axiom 1. And now axiom 2, and you see everything is symmetric. The axioms are symmetric. How I defined P and L is symmetric. How I defined the incidence relation is symmetric. So this means that finally also the same proof applies here. So this is completely analogously. Last not least, axiom 3, and you remember axiom 3 meant that you have 4 points such that no 3 of them are collinear with the same line, incident with the same line, and I just give you very concrete vectors that satisfy that. So in every field K, so whenever you have a field K, it contains at least a 0 and it contains at least a 1. So these here are vectors in our three-dimensional vector space, and they have a corresponding equivalence class, and I simply have to check that no 3 of them have a same vector at the same time with vanishing scalar product to any of them. But if you look at those vectors, any 3 of them form a basis in 3 space, and you can algebraically check that axiom of 3 holds as well. Please do that as an exercise if you need all the details. So, we learned about the Fano plane, and I want to show you that the Fano plane comes exactly from such a construction. So we get that construction for a specific field. The field that we need is that where the numbers are only 0 and 1, and all calculations are done modulo 2. So it's what people in algebra very often call the GF2. It's this field of 0 and 1, and you have addition modulo 2 and multiplication of modulo 2. So in particular, 1 plus 1 is 0 in that field. And, well, how many vectors do we have in k to the 3 that are different from the 0 vectors? Well, for each entry here, we can either write a 0 or a 1, though we get all together those 7 vectors. We should for a moment think about equivalence classes, well, we said we identify non-zero multiples, and in that field here, the only non-zero element we have is the 1 that we have here. So in an equivalence class, there is only one element. So in that case, if we have an equivalence class, the only thing in that equivalence class is the element itself. So we have nice representatives of all equivalence classes. No two of them are equivalent, and so they must represent the points of our projective plane. So now look for a moment. I sorted those vectors in a way such that I have, well, no zeros in those slots here, and that I have zeros everywhere else, but I have no zeros in that slot, and again a 0 here and 1. So I sorted them in a way such that those with 1 in the last entry come first, then comes those with a 1 in the second entry, and then finally 1 in the first entry. And if you look at that, well, n is 2 in our case, so this will be a projective plane of order 2, and for each of the entries here we have 2 choices, which all together makes 2 square possibilities here, 2 possibilities here, and 1 possibility here. And so you see how this number 2 squared plus 2 plus 1 reproduces in that case. So let me associate those vectors to the Fano plane, and let's once more construct the Fano plane. And we said the construction of the Fano plane started with those 4 points that come from axiom 3, and now I do exactly what I did before when I said take those 4 points as being the 4 vectors of axiom 3. So you see these 4 points can be associated with the first 4 coordinate vectors. Then we see that those 2 lines here have to meet in that point. So what do we need here? We need a point that is on the same line as the other 2 points. So in other words, those 3 points in our k to the 3, the representants, have to be linearly dependent, which means we need a vector here that is linear dependent to those pair, and well, there is not much choice in our situation. So if we add those 2 vectors, you remember 1 and 1 is 0, we get a vector 1, 0, 0, and exactly that is a vector that we have to put over there. And you see magically it works also for this and this. If we add those 2 vectors, then we get this vector here. The 1 reproduces, and this 1 plus 1 gives 0, this 1 plus 1 gives 0. Similarly, we can get this vector to be the 0, 1, 0 vector, and last not least, the intersection here at that point, this one here, will be this vector. Just make the check. If you add this vector and this vector, you have a 1 here, which cancels the 1 here, and you get 1, 1, 0. And if you have this vector and this vector, you see you get a 1 from here, you get a 1 from here, and a 0 from here, which is a perfect match. So you see, the Fano plane is nothing else as the projective plane over a very, very simple field. we should perhaps check whether the last line here is satisfied as well, but you see this works as well. This one plus this one gives this vector here. How to continue? So let's take the next more complicated field, which is the field that consists of numbers 0, 1, 2 and all calculations modulo 2. That's what people call the GF3. So for every prime number you have such a GF here. GF is the approximation for general field, and so here are representatives of the equivalence classes. So now we have to look for a little moment that I'm doing the right thing. So I said I identify scalar multiples of vectors. So if you look at the first vector here, it doesn't matter whether I take the vector 0, 0, 1 or the vector 0, 0, 2. Will be the same equivalence class. So I only need one of those representatives. So I can freely take one of the entries here and norm it down to be a 1. So I did essentially the same as I did before. I normed down the last entry here to 1, and you see the other entries that you have up here, they can be chosen freely, and I get those choices. I have 3 elements in my field, so I get 9 choices altogether. So this here are 9 vectors, which is essentially 3 squared. So here I have the second entry normed down to 1. The last entry here cannot be normed down to 1 because it's 0. And you see I have altogether 3 choices here. And last not least, here I have the vector with 1 entry in the first spot and 2 zeros below it, and you see it's just one representant that I get here. So all in all, I get 3 squared plus 3 plus 1 is 13 points, and I took a copy of a drawing of this incident structure that is in the book. So if you look here, you have the 9 points here and the 4 remaining points here, and I really encourage you to check that this thing that you see here has really the same incident structure as you get from this nice plane here. So we found the next more interesting finite projective plane. You see on each of those lines you have 4 points. So 1, 2, 3, 4 here, 1, 2, 3, 4 here, and for instance 1, 2, 3, 4 here, and 1, 2, 3, 4 here. I think you get the idea. Also here, this is an extremely beautiful object, and I want to show you at least one more drawing of it that was done in context of a thesis written by one of the participants of one of the projective geometry classes in the last years. It was Julia Martini, and she came up with the following beautiful drawing of the same incident structure, and you see it also has such a kind of cyclic symmetry as we found it in this Fano plane, and it seems to be the case, I'm not completely sure about it, but it seems to be the case that every projective geometry that comes from a prime number field has this property. So you see, by now we already know 2 different finite projective planes, and a natural question that arises is Is that all? Are there many more? And well, obviously there are many more, because for every finite field, we get a finite projective plane. So as the next thing, uh, let's consider finite fields, and let's make a little excursion to algebra. And you should have learned at some point that if you take the numbers from 0 to p minus 1, where p is a prime number, so I should write down p is a prime, then it turns out that this here is again a field. That's a GFP. So we get finite fields for every prime number, and as a little bit deeper result in algebra, we also get that there are finite fields for all powers of prime numbers. So there are finite fields with 2 elements, there are finite fields with 9 elements, there are finite fields with 8 or with 27 elements, and for each of them we get a projective geometry. And again we can ask, are these all the projective planes? And now let me do a little investigation of, well, the first small numbers and whether we get projective geometry for them or we don't get one of them. So let's see for which of those numbers there exists projective geometry of that order. And before I do that, I want to quote a theorem, a really famous theorem of two people, Bruck and Reiser, proved in 1994. And they proved the following thing, which actually is a really deep theorem. If the order, and let's n be the order of the projective plane, of a finite projective plane, if this order is either 2 modulo 4 or 1 modulo 4, then this order can be written as the sum of 2 squares for integers I and j, where in the integers I also include the number 0. And with this knowledge, let's now see what happens in those cases. So these here are the orders, and we already know that there is a projective plane of order 2, which comes from GF2. And well, as a matter of fact, 2 is also 2 modulo 4. Those 2 must be possible to write as the sum of 2 squares, and you see it immediately. It's 1 square plus 1 square. So how about 3? For the 3, we also know that there is a corresponding field, and we already saw a picture of this projective plane. 3 is not 2 or 1 modulo 4, so Bruck and Reiser doesn't tell us much. So how about the 4? The 4 essentially is a number for which we also get a field. We get the field GF2 squared, and well, that's a nice object. And if you want to have a nice exercise or a nice challenge for your bachelor thesis, please draw a really beautiful picture of this object, and perhaps draw many beautiful pictures of that. So how about 5? 5 is a prime number, and we are done with GF5 here. 5 also turns out to be 1 modulo 4, so Bruck and Reiser must also tell you something, and actually the 5 is 1 plus 2 squared, and everything is nice. 6 is the first interesting case. So how about the 6? 6 is 2 modulo 4, and it's neither a prime nor a power of a prime, though this may be a candidate for a projective plane that doesn't come from prime number or power of a prime number, doesn't come from a field. But 6 cannot be written as the sum of two squares, and 6 is 2 modulo 4, so Bruck and Reiser really excludes that case. So this here is really excluded by the theorem of Bruck and Reiser. Let me continue a little faster. 7, well, it's GF7. 8 is GF2 to the power of 3. No Bruck and Reiser applies here. 9 is perhaps a little bit interesting. So 9 is GF3 to the power of 2. Bruck and Reiser applies, and in fact, and now I really need that we have the 0 included in our natural number. The 9 is turns out to be 3 squared plus 0 squared. Next interesting case is 10. So let's have a look at 10. So 10 is it's 2 modulo 4, so Bruck and Reiser applies. But 10 can also be written as 3 squared plus 1 squared, so Bruck and Reiser tells us nothing. And so we really have a candidate of a projective plane coming from a situation where we do not have a field. And actually what happens is it can be proven that there is no projective plane of that order, and can be proven means it has been proven in the late 70s by massive computer powers. One or the other of you may know the computer which is called a Cray. Cray was a supercomputer of the early 80s and late 70s, and the proof here was 2000 CPU hours on a Cray. Another interesting topic for a bachelor thesis: try to do that on your iPhone because or on your smartphone, because a smartphone outperforms today what was a supercomputer in the late 80s, and so it may really be an exciting thing to redo that. So this here is really one of the really interesting cases. So then comes a boring case. 11 is just GF11 because 11 is prime, and 12 turns out to be open. 12 is not modulo 2 or 1, not 2 or 1 modulo 4, so Bruck and Reiser doesn't apply, and it's not a prime number, it's not a prime power, so it's really open. Is there a projective plane of that order? And nobody currently knows. So if you want to have a topic for your bachelor thesis, try to attach it, or your master thesis, or your PhD, or becoming a professor. I don't know how hard it is these days. Okay, 13 again is easy. That's GF 13 and so on. So far it may look like the following thing, that if you don't have a power of a prime number, then you don't have a field, and so far all projective geometries we know really come from fields. But this is not the case in general. So let me just quote a little from a web page. So the web page lists projective planes of small order, and you see here those are all So here you have the order on that side, and these are these PG2 something is a projective plane of a given order coming from a field. But if you look here with order 9, the first time it happens that there are other projective planes. So if you look at order 9 here, you see there's one case coming from the field, but there are also 3 other cases. So there are combinatorial objects that are projective planes not coming from fields. And let me just show you a little bit more of that table. You see here is a gap between 11 and 13, that's the unknown 12. There's a gap between 13 and 16, and it turns out that 14 can be excluded by Bruck and Reiser, but 15 is still open. But with 17, you still have plenty of planes. And here with 29 and 27, you also get many planes, and here with 49, you get hundreds of thousands of planes. So this is really an interesting and actually also applicable topic. What kind of projective planes exist there that do not come from fields? So far for the moment, this essentially concludes our first slot on homogeneous coordinates. And let me summarize so far. So we have seen that every field generates a projective plane, and in particular finite projective planes are interesting objects. So let me, as a placeholder for those statements, just show you the picture again of the projective plane with 30 elements of order 3. And we also have seen there are finite projective planes not coming from fields. And now we will leave the finite part of our lecture and enter the real numbers and deal with continuous structures in projective planes. See you in the next slot.